Welcome to the viewers. Now we discuss a more generalized form of Euler's theorem of two variables, especially for homogeneous functions. If let us write let V be the homogeneous function of x and y of degree n, then x square del 2v del x2 plus 2xy del 2v del x del y plus y square del 2v del y2, that will be given as n into n minus 1 into v. Now here conditions, all partial derivative of first and second order are supposed to be continuous. Now we are going to the proof part. Since V is the homogeneous function of x and y of degree n, then by Euler's theorem x del v del x plus y del v del y is equal to nv, giving it equation number 1. Differentiating partially of 1, with respect to x on both sides, we get here it's clear x del 2v del x2 plus del v del x plus y del 2v del x del y is equal to n into del v del x. And if we multiply this term with respect by x, then we have, taking it equation number 2, multiply 2 by x, we obtain x square del 2v del x2 plus x del v del x plus xy del 2v del x del y is equal to n x del v del x, taking it equation number 3. Now we differentiate once more partially of 1 with respect to y. So differentiating 1 with respect to y, we have x del 2v del x del y plus, actually del 2v del y del x, but since they are commutative by the Schwarz theorem, so we can say that x del 2v del x del y directly. And here it is with respect to y. Okay, del v del y plus del 2v del y2 is equal to n del v del y. Now multiply, taking it equation number 4, multiplying 4 by y, we have xy del 2v del x del y plus y del 2v del y plus y del 2v, here it is a mistake, sorry, y del 2v del y2, that is y square del 2v del y2 is equal to u ny del v del y, taking it equation number 5. So in the earlier stage equation 3 we get x square del 2v del x2 plus x del v del x plus xy del 2v del x del y equals to nx del v del x, and from equation 5 we have xy del 2v del x del y, y del v del y, and y square del 2v del y2. If we adding these two, that is adding 3 and 5, we obtain x square del 2v del x2 plus x del v del x plus y del v del y plus 2xy del 2v del x del y plus y square del 2v del y2 is equal to nx del v del x plus ny del v del y. So that is x square del 2v del x2, and it is for these two we are using Euler's theorem. It is a homogeneous equation of degree n, so it can be written as nv plus 2xy del 2v del x del y plus y square del 2v del y2 is equal to, taking n common, x del v del x plus y del v del y. That is x square del 2v del x2 plus nv plus 2xy del 2v del x del y plus y square del 2v del y2 is equal to n into nv. It is also homogeneous function of degree n. Here we have also putting this value, and it remains same, keep remains same, and here taking n common, then we get nx del v del x and ny del v del y, to taking n common, x del v del x plus y del v del y. Here we get this result. It is also homogeneous function of degree n. V is also the homogeneous function of x, y of degree n, so it will be nv by Euler's theorem. Here also by Euler's theorem. So finally we obtained x square del 2v del x2 plus 2xy del 2v del x del y plus y square del 2v del y2 is equal to n square v minus nv. So it will be written as n into n minus 1 into v. So finally we prove then we prove this result. It's a more general case of Euler's theorem, and sometimes we have to derive this type of results in the examination purpose also. And now today our discussions of Euler's theorem for homogeneous functions of degree n, and so today we end our discussion. Thank you.